Hello, this is lesson 13. This is our second lesson on transistors, third lesson on semiconductors. I want to start out by doing a quick review on how the transistor works. Remember, we describe it as a current amplifier, and using our fluid flow analogy, we can say a small flow of fluid into the base, this would be the base, controls a much larger flow of fluid through the main device. So we want to use this small base to control a much larger flow. As we just talked about last time, the device is more efficient if it's fully saturated. And we can think of it in this way, as in this case, if that valve is only partially open, some current will flow through, but it will be much more restricted than if the valve is fully open. So even in the pipe flow analogy, this pipe is more efficient if the valve is fully open. And that's how we're going to use it in this course. Okay, so remember, what is a transistor? Here we're talking about the bipolar junction transistor, a BJT, which is three semiconducting materials sandwiched together, N-type, P-type, and N-type. Remember, we have a base, a collector, and an emitter. And current, small amount of current flows through the base, much larger current flows through the collector, and the total current, the current coming out of the emitter, is the sum of those two base and collector currents. In order to get the device to operate, we have to set it up in a circuit in such a way that everything is correctly forward biased. So here we see forward biased definition. So the voltage from base to emitter, that's here, has to be at least 6 volts. That should really be a greater than 0.6 volts. And usually the voltage from the collector to the base will be higher. The voltage at the collector must be higher than the base. And like I say here, typically much more. This is usually going to be a high voltage source, so maybe it's like 12 volts or something. And then we'll get a VCE voltage to collector to emitter voltage drop of about 0.2 volts when we're in saturation mode. Now again, this is a current amplifier, and that's what this equation defines. So remember, beta is gain, which is the basically the multiplication factor of the current. So here's the current into the base, and then it's multiplied by this gain, and the current through the collector emitters leg of the transistor will be a function of that base current and the gain. Again, when we run this, we want to run this in saturation mode, in which case the base current will be fairly high and we'll get a high flow of current from the collector to the emitter. Now, if we want to understand how these devices operate in a certain circuit, we need to figure out its operating point. We use a chart like this, which is a load line chart. This family of curves, these we call isolines, indicate different base current values for a given transistor. And we determine where it's operating by looking at the circuit that it's set up in. So let's take a look at that. Let's review that really quick. So this was really the purpose of last lesson, was to understand how do we figure out where a transistor is operating for any given circuit that it might be in. So we start by figuring out what the base current is. And how do we do that? Well, we use Kirchhoff's voltage law. So let's do that right here. So if we looked at, this is the base circuit, base to emitter circuit. So we have this voltage source, Vs. We have a voltage drop across the resistor. So the base current times the base resistor. Then we have the VBE voltage drop, which we assume is 0.6 volts, and then that equals 0. So now we can easily solve for the base current is going to be Vs minus 0.6 volts divided by the base resistor. And once we know that, we can select which isoline this might be on. Remember, there's a family of these lines, and so we would figure out, we're on this one right here because IB equals whatever value. Okay, this thing's freaking out on me. Whatever we calculated here. Okay, next we need to plot this load line, and we do that by using some kind of going through a thought experiment. So the first one would be to say, what if the collector current were 0, meaning we're on the bottom of this chart, so we're along this axis. If the collector current were 0, if IC equals 0, then that would mean that the voltage drop from collector to emitter would have to be the entirety of whatever this voltage source is. Because remember, if there's no current flowing through the resistor, then the resistor voltage drop must be 0. So that means the total drop, looking at Kirchhoff's voltage law, would have to be V0. So then we can just plot this point as whatever this source voltage is up here. Next, we think about, what if VCE was 0? That would put us on this vertical axis. And that happens, when that happens, that means that the collector current, IC, has to be defined by this relationship. So we'd say IC has to be completely dropped through this resistor. So it's got to be VO divided by RC. And that tells us that point. So then we just draw a straight line between those 2 points, and the intersection of that load line, we call this the load line, with the base current ISO line is our operating point. In this case, that's Q. Okay, so that tells us how to figure out what a transistor is doing if it's in a given circuit. What we'd like to do as engineers is ultimately design a circuit to ensure that the transistor is operating how we want to operate it. And that's what we'll go over next. Before I do that, I just want to reinforce a couple more points. We talk about how there are 3 operating regions for the transistor. First is the cutoff region, which is basically saying it's not on, it's not doing anything. So we don't really care about that. Then there's the active region. If we were electrical engineers and we're designing other components, we would care about the active region, using it as an amplifier. We're not going to operate in that region either. In this class, we want to be operating in the saturation region. This is what we want, because this means that the device is being as efficient as possible. Usually this here is going to be some kind of load, something that we're trying to turn on and off. So this could be, we're going to use it to turn on a motor. It could be a light, could be a speaker, could be any number of things. So this could be motor or other actuator. There's lots of actuators you might use, you might turn on with a transistor. We want energy into the load. We want the energy going in here. We don't want it in the transistor. That would be a waste. Okay, so we get the least waste if we're operating in the saturation region. And I'll prove it to you really quickly. So here's some analysis. If we look at a basic operating chart for a transistor, and we consider these different operating points. So notice this load line would apply to a given circuit configuration. If we had certain VS and V naught voltage sources and resistors, then I started maybe turning down the base resistor in order to increase the base current, or it could be turning up the base voltage to increase the base current. So either way, we're going up from line to line to increase the base current. So as we increase the base current, the operating point moves up this ramp towards that saturation region. So if we look at some actual calculations with that, here's a simple Excel spreadsheet where I plotted these different base currents and then calculated what the resultant collector current would be. Remember, collector current is the current going through the device, but it's also the current going through the load, which is where we want our energy to go. So we see that the voltage drop across the transistor and the voltage drop across the load. And then I calculated power by just doing, remember, power equals V times I. So that tells us the power going into the transistor and the power going into the load. And here's a plot. So notice, as the base current goes up, the power that is lost in the transistor, the blue line, decreases. And we get the maximum power through the load when we have the highest possible base current. Okay? And that's when we're up here in the saturation region. So that's why we want to be in saturation. Okay, that's that again. All right, so how do we ensure that our transistor is always in saturation? And that's really the subject of today's lesson, is how do we design a transistor so that it will be in saturation? So first step is we're going to make a bunch of assumptions, basically make 3 assumptions that we're going to call rules of thumb that we use to design a transistor to be in saturation. So the first thing we're going to do is we're going to assume a voltage drop of 0.2 volts across VCE, okay? We need to know this so that we can calculate what our resistor needs to be in the collector circuit to get the IC that we want, okay? So let me back up a little bit. So in this scenario, maybe I hand you a transistor, and we're going to do an example in a second. So I hand you a transistor, and I say, you've got a certain voltage source, and you've got some load that I want you to power with it. And so the load, maybe you look up on a data sheet, or it has some requirements, it probably has some required current that it needs. So we want to make sure we have a certain amount of current going through a load, and we want to specify that. So you're given a transistor, you're given some voltage source and a desired current, and then you're probably given a given base voltage, and you need to pick resistors to get the transistor in saturation. Okay, so given that, these are the rules of thumb we use, or assumptions we're going to make. We're going to assume a voltage drop across VCE of 0.2 volts. That allows us to apply KVL to this branch of the transistor. Next, we're going to assume a gain beta of 10. And this is a good rule of thumb for standard transistors. And we'll see in the lab that you may not actually have that exact amount, but by doing that, that assumes that the transistor is operating in its saturation mode, and which is what we want. So we assume it's saturated, and we treat it like it's saturated and do the calculations, and it will be saturated. Okay, so given the gain, we can use the current, collector current IC that we calculated in the previous step in this formula to get the desired base current. Desired base current. Okay. Once we know the desired base current, we assume a voltage drop from B to E of 0.6 volts, which would be true if it's in saturation, and that allows us to calculate the required base resistor. So let's do an example. Okay, so here we see an example scenario where you're given a load, and we're told, given a load, put the transistor in saturation given the circuit constraints here. So as I said, first we're going to calculate the necessary collector resistor, that's this guy, for the desired collector current. And then next we're going to calculate the required base current that we need in order to ensure saturation. And off of that base current, we're going to calculate the necessary base resistor to get that base current. Now, this could be set up in a different way. So in this scenario, you're given the voltage sources and a desired current. It's possible I could tell you, I'm giving you the base resistor, and I'm asking you to find Vs right here in order to get the transistor in saturation. In either case, it works the same way. Okay, so here's an actual example. So this is problem 10.11 from the book. So we're asked to design a BJT circuit to switch an LED, and we want the switch or the transistor to operate in saturation. And we're told the LED has a 2.2 volt voltage drop, so it's probably a green LED, and we want a current through the LED of 100 milliamps. And we're told V naught is 5 volts and Vs varies from 0 to 3 volts and use standard resistors. So take a look at that problem, think about that. Okay, so let's work through this. So the first step, number one, we need to use KVL in the collector circuit. So let's see, we have V naught. So let's just write it out like this: V naught minus VLED minus, then we go through the resistor. So that's IC RC. Then we go through the transistor. So minus VCE equals 0. So now we can plug in what we know there. V naught is given as 5 volts. VLED is given as 2.2 volts. 2.2 volts. Then IC is given, we have a desired collector current of 100 milliamps. So I'll just go 0.1 amps times RC, which is unknown, that's what we're solving for, minus the voltage drop from C to E. Remember, this is one of our rules of thumb. So the first one there, so we insert that 0.2 volts equals 0. Then we do some algebra and solve, and we get collector resistor, a desired collector resistor, excuse me, of 26 ohms. If you do the algebra, you'll see that. Okay, next step, step 2, find IB for saturation. So again, now we use our gain equation. So remember, IC equals beta times IB, and we assume a gain of 10. So that's our second rule of thumb. So if we do this, we get that the base current, just do some algebra here, is IC divided by beta, which is 100 milliamps divided by 10. And so the base current needs to be 10 milliamps. Let me just separate these here for us so we don't get confused. Okay, step 3, we have the base current. We need to find the base resistor. So we've got a base current here of 10 milliamps. We've got 100 milliamps here. So again, we use my favorite technique, KVL. So we have Vs minus base current times base resistor minus the voltage drop from B to E. That's our third rule of thumb. So substitute in 0.6 volts. Whoops, or I was going to do, leave this kind of generic here. Then we'll sub stuff in later. So this is VBE equals 0. Now we do our substitutions. So Vs was given as varying from 0 to 3 volts. So we'll put in 3 volts here, assuming we're at the max value. IB is 10 milliamps. And RB is what we're solving for. Minus 0.6 volts equals 0. So solve for RB, and that equals 240 ohms. Okay, and so that's we've at this point we've fully designed the circuit. We have picked 2 resistors, the collector resistor and the base resistor. These guys were all given, so we don't need to know those. So there you go. That's how you design a circuit to make sure it's going to be saturated. And when you're done, you can use the previous load line analysis to check and make sure that it's actually saturated. And we'll do that in the lab and we'll test it out. Okay. Here's a data sheet for a transistor, and we'll talk about this a little bit more in class and in the lab. But you see this is a little bit backwards from what I've been showing you before. Here we have base current plotted along the horizontal axis, and we have collector emitter voltage here. We're looking at an inverse way before, and then the ISO lines are the collector currents. So in this case, this is where the transistor is saturated, because as you see, as you increase more base current, you're not going to get that much more collector current. And you also see this is the region where VCE is the smallest. So that's what we want. That's the region where the transistor is most efficient. Okay, so let's summarize this. We'll do this board work in class tomorrow. So you should be able to answer these questions. A transistor has 3 operating regions. What are they? So we talked about cutoff, active region, and saturation region. And for most mechatronic applications, we want the transistor to be a switch. What region is that? That was our quiz. And that's where we get the lowest power consumption or most efficient. Okay. So here's another example problem. You could attempt to work that out if you like. We will do this board work as an exercise at the start of class next time. All right, thank you for your attention. That's the end of this lesson.